Welcome to the PhotoModeler Vehicle Crush tutorial. In this tutorial, we will determine crush measurements on a vehicle using photographs taken from an unknown camera. Using these two photos taken using an uncalibrated and unknown camera, we establish the amount of crush at certain key points. Since nothing is known about the camera that took the crush photos, to be able to solve this project, you must have some known information about points on the uncrushed part of the vehicle. This exemplar vehicle is surveyed to extract 3D coordinates to be used as control points, which are needed by PhotoModeler's inverse camera to solve for the unknown camera parameters. This information could also be measured using other survey instruments, such as a total station or a laser scanner. In this case, PhotoModeler was used with a calibrated camera as a surveying tool to extract the 3D coordinates from the exemplar vehicle. Any method that can generate an accurate set of 3D coordinates can be used as a source of control points. Here is the completed exemplar vehicle project that was done with PhotoModeler and a calibrated camera. This process is similar to the steps outlined in the Manual Points Project tutorial video. This project uses 6 photographs taken from a variety of angles. The residuals are low, and the project is solving well. Some measurement checks were done against the exemplar vehicle. This ensured a strong result and therefore a good set of control points, which in turn increases our chances of a good inverse camera result. We export the project as a DXF file, which will be used in turn as our control data for processing the photos from the unknown camera. We go to File, Export, Export Model, and select 3D DXF. We make sure the point IDs are on, and then save the file as corollaexemplar.dxf. Next, we start a new PhotoModeler project to work with the photos of the crushed vehicle from an unknown camera. We choose a manually marked project, then browse to the folder with our images and add them to the project. Since we do not know anything about the camera that took these crushed photos, we choose an unknown camera solved by control points. We click Next and get a message telling us that an inverse camera cannot be shared by 2 photographs. Since we do not know anything about the photos, we cannot assume that they were taken by the same camera or at the same focal length. This message tells us that a copy of the camera description has been made. We now have 2 cameras in the project, each assigned to a separate photograph, allowing them to be solved independently. The message also tells us the focal length flag has been set. This means that the focal length option in the photo properties is set to be solved when inverse camera processes. We can see and adjust this using the Photo Properties dialog. In certain cases, you may want to solve the principal point as well as the focal length. This may be necessary if you think the photographs have been cropped and the image is off-center. Solving principal point requires a very strong set of control points, so we suggest you solve just the focal length at first. The format aspect ratio is not often solved in inverse camera, and you solve it only if you suspect there is a scanner error or some other problem that would affect the squareness of the pixels. When working with photos from an unknown camera, something needs to be known about the scene so PhotoModeler can calculate information about the camera. In this case, we will use known 3D XYZ locations imported as control points. To add the control points, we open up the Imports and Coordinates pane and press the Import Data button. Choose Control the Solution, then Using and Adding Points, Lines, and Surfaces from a file. Click on the File Name Field's Browse button and select the corollaexemplar.dxf file that we had exported from our exemplar vehicle project. This data could also come from a third-party survey or other source. Under the DXF-specific fields, you can choose how the DXF text fields are handled. Since we included point IDs with our export, the text fields will contain the point IDs, and we check DXF text fields are point names. The units are inches. Set the points to be fixed to ensure that the control point coordinates are not adjusted during processing. This is suitable when you will mark a low number of control points. Turn on Merge Vertices so that any lines which end at the same location will only create a single point. With large imports, this step can be time-consuming, so can be left off. Selecting the Next button will import the DXF data as control and sets the project units 2 inches. This is a list view of the imported points. Use the 3D tab to see a 3D view of the imported model. This model contains more points and details that is normally required to solve a control point project, but this detail will help demonstrate other aspects later in the tutorial. If we scroll the list, we see that all the points have ID numbers. There is also a name column. The ID numbers are in sequential file order. The name field comes from text entities in the DXF file. In this case, the numbers are the point IDs from the exemplar project. If we had used the renumber command before exporting the exemplar DXF, the 2 IDs would match up. You can see some ID names have text describing the point. These particular points have been named in the exemplar project to help us identify the points more easily when we mark the control points on the photos. For example, this point. Point 107 in the exemplar project is named DS front rail, which is short for the front part of the rail molding that runs down the driver's side of the car. We select the front rail point. If we switch back to the 3D view, you can see the front rail point is highlighted in green. You can select points in either the 3D or the list view. We open photo number 1, where this point is visible. We'll activate Control Mark mode and move over photo 1. The cursor switches to the import marking icon. Hold down the Alt key to bring up a zoom window to take a closer look and mark this point. Next, we will mark a point near the top of the door. Incorrect or inaccurate control point marking will give poor results in inverse camera processes. If you incorrectly mark a point, you can adjust its position in Select mode. To see the list and 3D view of the imported points, drag the 3D tab and use the docking indicators to place it in a new location. The User Interface Overview video gives more details on arranging panes. Next, we mark this point. It is very important that the control points have good coverage on the photo. You want to have control points marked across the photo rather than all bunched up in one area. Especially when solving focal length, you should have some points with varying depth. Otherwise, you may get poor results, or inverse camera may not solve at all. All our points so far are covering this one plane of the driver's side. This point, passenger side C-pillar bottom window, represents a point on the other side of the car. This can be viewed through the windows. We now have some depth coverage in the photo. Enough points have been marked for the project to process. The camera's position and inverse camera focal length have been solved. This processing has been done using the minimum number of points. If the points marked did not have sufficient spread across the photo, you may get an orientation failed message. In this case, you would confirm the points marked so far are correct, and possibly mark more points to strengthen the project before the orientation succeeds. Here, on photo 1, we have marked additional control points on undamaged parts of the vehicle to strengthen the project's solution. We have reviewed our marked locations and checked the residuals to make sure the project is solving well. Another check we can do to ensure the project is solving correctly is to turn on the 3D projected model and check that it lines up with the photos. Go to Visibility. Turn on Imported Points and Lines. Overlaid on the photo are the lines from the imported control file. We study the photo to see how well the control file matches the vehicle in the photo. The marked control points have been used to lock the rest of the control file in place. Of course, the projected lines in the front area will not match the crushed area, but the uncrushed area should match correctly. We check how well the lines match up along the windshield, the windows, and the doors. Since everything lines up correctly, the Locate button can be used to help identify where additional points can be marked. We will turn off the 3D display and open a point table. Our review of the mark placement improved our residuals. In an inverse camera project, residuals can be judged differently. Unlike standard reference points, in this project, we're solving the camera parameters using control points that are set so that their coordinates cannot be adjusted. If we're not fully confident they are marked in the correct position, this can result in higher points residuals. For these types of projects, residuals around 10 pixels are acceptable, but lower would be better. When residuals reach 15 pixels and above, then you should review your control points to see if they are positioned correctly. The residuals in this project are acceptable, so we close the point table. We can now mark control points on Photo 2. Close Photo 1 and open Photo 2. Since this photo is not yet oriented, we cannot use the Locate tool. The first group of points needs to be manually identified. Switch to Control Marking mode. Again, we start with points which are easy to mark and have a good spread across the photo. Start with this point here and add points that give good spread across the image. This point we can see through the window here. This one we can also see through the window here. To make sure we have a good spread across the photo, mark this point here. The minimum number of points has been met, and Photo 2 is now oriented. We will mark some additional control points to strengthen Photo 2. Since the photo is oriented, the Locate button can be used to find locations for the additional control points. Here we have Photo 1 and 2 marked with a good set of control points. We've reviewed the residuals of the project, and it is solving well. If the lens had large distortion, more control points could be used with the camera optimization step to account for additional camera parameters. We will demonstrate a technique that can be used to verify the project's solution. We switch to referencing mode. We mark a point at the cross of this T. We move our cursor to the other photo, which becomes the destination window. The reference helper line, also called the epipolar line, appears. We can see that this line goes through the same point on the other photo. The reference helper line helps us find the intersection where we should mark the matching point. We mark the point at this intersection. We will try with another point. We mark the intersection of the T on the window here. Go over to our destination and see if the reference helper line matches up. If the reference helper line appears off target, such as up here, this is an indicator that the project results are poor. If this was the case, then we would have to review the placement of our control points and ensure we have sufficient control points with good coverage across the photos. If your project has large residuals and projected imported model, or reference helper line is not lining up, check your control point placement. You should also make sure that the exemplar vehicle that you got the control points from is the exact same model. It should be the same make, year, and model. Even some minor features such as body lines and molding can vary in shape or location in the same models due to dealer options and production variations. If we open a 3D viewer, we can see the imported control object as well as the points we have marked on the photos. Here are the 2 points we just added at the T intersections. The points marked on the photos are displayed in white. The imported exemplar points and lines are displayed in the default orange color. These materials can be adjusted at any time. We turn on camera stations and verify that they are in appropriate positions. We have performed our quality checks and are satisfied with our results. We can now move on to the next step, which is marking and referencing of points on the damaged section of the car. Now the inverse camera photos are solved. Using our control point data, we can continue with the project in the same way we would if we had a calibrated camera. We start by marking some of the damaged area of the hood, zooming in to make sure the points are marked accurately. Mark some holes and some parts of the bumper and undercarriage. When marking is complete, we switch to select mode and use drag region select to select our newly marked points. When we switch to reference mode, because points are selected, Photo 2 becomes a reference source. And we can reference the selected photos on Photo 1. We use the epipolar reference helper line to help identify where to mark the references. These points have now been referenced. Our final goal in this project is to get displacement measurements from a profile of the interior bumper shown here. The plastic covering of the bumper has fallen off, so we will use the inner bumper as our source of crush information. We use Image Enhance for a better view of this bumper in Photo 2. There are not many distinct points to mark on the bumper. We'll mark a point along the top edge of the bumper near some other identifiable feature, so we have a general idea of its location when comparing to the other photo. After we mark a point, we then move the cursor to the other photo and use the reference helper line to find where it intersects the bumper near the feature. We continue marking some key features on the bumper, using the reference helper line to identify the matching location on the other photo. We switch to line mode and connect the points. We have created the initial profile of the bumper. The bumper has now been modeled in more detail, while some points have been added on the hood for a complete model. We now have a top-down view of the marked data and control lines. The orange lines represent the control file, while the white points and lines show the data we marked. The control file also shows this extra line that has been added at the level of the bumper. This line was added so we could do profile measurements. This extra line can be added to the DXF file using a CAD package or in a text editor in some cases. We hit Reset to go back to the top-down view. We zoom in on the area on the front bumper. We want to get displacement measurements from this line to these bumper points. There are a couple methods for doing this. You can do certain measurements right within PhotoModeler, or you can export the model to a CAD program. If you're using a technique where you want equally spaced measurements on your crush profile for doing your delta V calculations, it might be easier to export the crush project data to your CAD program in the form of a 2D DXF file. You can compare the extracted crush lines with the 2D DXF profile of the exemplar vehicle and do the equally spaced measurements within the CAD program or even on a plotted drawing. To do the measurements in PhotoModeler, we open the measure plane. Our scale was defined by the imported control points. We select the control line, press Shift, and select this point on the bumper. A distance of 26.226 inches is displayed in the measure pane. This is a straight displacement measurement, representing the closest distance between the point and the line. This information can be cut and pasted from the measure pane to use in another application or for a report. This concludes the crush measurement project using photos from unknown cameras. We can complete such a project using the control points and inverse camera tools. We demonstrated how to import and view control data, mark control data to help solve inverse camera, check the quality results, and lastly, perform measurements within PhotoModeler.